Yeah, so without further ado, let us welcome the first speaker of today's session is Pablo. Pablo Jarillo Herrero. So not Jarillo Herrero or
He speaks perfect Spanish, actually. Thank you. Okay, hello everyone. It's a great pleasure to be here to celebrate Allan and his many contributions to physics. I was trying to think about my first memory of Allan, and I think you don't know this. Oh, you may remember this anecdote or not, but so, this was at the APS March meeting in 2000, sorry, not 21, 2001. I don't know, my finger slipped, 2001 in Seattle. I had arrived a couple of years earlier to UCSD in 1999. I wanted to be a high energy theorist. I did my specialty in my undergrad in Valencia in Spain in high energy, and I wanted to be a high energy theorist, and they had a good program there. This is what I looked back then. This is the only picture I have. Sorry, it must have been some party. And then, I met Joaquin Fernandez Rosier, who, he tried very hard to convince me to convert to condensed matter. He was a postdoc there with Lou Sham, and he was doing, he was telling me about all this great, very interesting work which was going on spintronics. And there was this guy, Allan MacDonald, who was leading it. He was a theorist, and he told me he wanted to become a postdoc with Allan. This is, this is not a picture of back on the days. This is a picture from last year, actually, in London when I met Joaquin. I don't have any picture with Joaquin from those days, but so he applied. I was trying to decide what to do. Should I stay high energy theorist? Should I convert to condensed matter? And he told me, let's go to the APS March meeting. You're going to meet a lot of condensed matter physicists, and it's going to be great. And also, I have applied for a postdoc to Allan MacDonald. Now, a few days or a couple of weeks before the March meeting, he tells me, you know what? Allan MacDonald told me he doesn't have any funding, so I'm not going to be his postdoc, So it was a big bump, but we still went to the March meeting. And then Joaquin gave a very nice talk. And Allan was in the audience, camouflage there, wanted to check Joaquin. So after the talk, Joaquin and I get out of the room, and I don't know if you remember this, but Allan shows up and says, Joaquin, you have an offer from me. And Joaquin said, but I thought you didn't have any funding. And then Allan said, I changed my mind. I remember those words. Those were the exact words. I changed my mind. And then I thought, this was the first lesson I learned from Allan. Okay, you always say you don't have funding for postdocs, but you can always change your mind, So anyway, Joaquin came to Austin to become a postdoc of Allan. And then, I visited him. I met Allan briefly. He probably doesn't remember me, from back then. But you do? Okay, great. and then, of course, I have met Allan many more times, including visiting Austin a few times. So yeah, you had some small part in seeing how cool this whole process was. Tilted me more in becoming a condensed matter physicist. So yeah, of course, your influence was much greater later on, but that was important initial seed. Okay, so. I want to tell you about molecular quantum matter, and I think many of you are familiar, but I know that this is a very broad, because Allan has made so many contributions to so many fields and areas of condensed matter physics that I know this is quite broad, and some of you may not be that familiar. Okay, so let me just give you a little bit of an intro. So, traditional quantum materials, they have length scales, atomic length scales, sort of an angstrom, and we have hundreds and hundreds, thousands of these materials. Okay. They can be very challenging to study, especially when many body physics is involved. And as a result, additional platforms, complementary platforms have been developed to investigate strong interacting physics and topological physics in materials. About 20, 25 years ago, ultra-cold atoms in optical lattices were developed. There, the length scale now is a micrometer because that's the wavelength of light. You create a periodic potential with lasers where you load atoms, and you can tune and control, every parameter in the system with exquisite precision. Okay, so this is something where you have a lot more control than with traditional quantum materials, where you have to grow a different crystal each time you want to explore, a different property. And then, a few years ago, what happens is that a new platform, Moray quantum matter, was developed. This is nicely complementary in length scale, for example. The typical length scale now we're talking about is of the order of 10 nanometers, and which is about a couple of orders of magnitude, from either of these other platforms. Associated with the length scales are also energy scales. Yeah? So in quantum materials, 100 to 1,000 Kelvin for many values of the parameters of the system are standard. Here in cold atoms, it's more like 0.11 nanokelvin because distances are much larger. With Moray quantum matter is 1 to 100 Kelvin, which is a very comfortable temperature scale or energy scale to explore in a solid state physics laboratory. And it is also complementary in the degree of control. Yeah? So we don't have quite as much control as with the cold atoms, but we have quite a bit more than with traditional quantum materials. And on the flip side, with cold atoms, because the temperatures are still relatively high, it has been very difficult to realize many of the phases of quantum matter that people are interested in. However, with Moray quantum matter, we have realized many, many of them, and including new ones, as I'll show in a moment. So, initially, the thing that developed this trick of Moray quantum matter was something that has become known now as twistronics, which is the fact that with 2D materials, with the advent of 2D materials, we can do something that was impossible to do before in the history of material science, which is to change, to choose what angle you want to have between the crystalline planes in your solid. Okay, so in particular, you can have a sheet of graphene, and you can put another sheet of graphene on top with any angle of rotation that you want. This animation goes a little bit slow on the screen here in Zoom, and this creates a Moray pattern where the Moray wavelength, the distance between these, regions let me actually just flip this, between these regions is sort of inversely proportional to the twist angle, okay? And with this, you can realize many things. In particular, over the span of just maybe 6 years now or so, we have been able to realize pretty much all of the phases of quantum matter that we know, okay? From exotic correlated insulators to unconventional superconductors, many topological phases, magnetism, quasi-crystals, new types of ferroelectrics, strange metals, generalized Wigner crystals, acetonic insulators, pneumatic systems. Pretty much every phase of matter that you're interested in has either been realized, and a few new ones that didn't exist before have also been realized with these systems. And this is using very simple materials, maybe graphene and hexagonal boron nitride, maybe some twisted transition metal like chalcogenides, with very simple elements. So what do I want to tell you about today? I want to start by giving you, again, especially for those that are less familiar with this field, some of the highlights of I call the rise of Moray quantum matter of this field, in these past few years, what has happened, And then I will focus a bit more for the specialist, and I will tell you about our recent simultaneous transport and tunneling spectroscopy measurements of Moray superconductors, okay, where we have observed the superconducting gap clearly, and we have signatures or evidence of nodal superconductivity in the system. So let me get started with this, and start with magic angle twisted bilayer graphene. So graphene has in the electronic structure Dirac cones, and if you have two layers, you have the Dirac cone of layer 1 here and the Dirac cone of layer 2. If your angle, the twist angle between the two graphene sheets is small, the Dirac cones of each layer are separated a small distance in momentum space, which is proportional to the twist angle. And this would be the situation that would be realized if the electrons in one graphene sheet did not know about the other graphene sheet, okay? However, because when we place graphene on top of graphene, these two graphene sheets are just 3 angstroms apart, electrons are very much aware that the other graphene sheet exists, and in particular, they can tunnel between the two graphene sheets, okay? That interlayer tunneling leads to bond repulsion there at that energy of that crossing point. This is the same as bonding anti-bonding states for the hydrogen molecule, but this is bonding anti-bonding bands for this bilayer graphene molecule. Okay? And this is the situation when this interlayer tunneling is much smaller than the energy of that crossing point. But if you decrease the twist angle, okay, at some point, this lower band that gets pushed down in energy gets pushed down all the way to 0. okay? And that happens when this interlayer tunneling is approximately the energy of that crossing point, yeah? So we say that a flatland condition has been realized and is reached at an angle, which depends on that interlayer tunneling, and which was coined by Rafi, who's here also, and by Allan as the magic angle, okay? And it happens to be 1.1 degrees for graphene on graphene. So this was, the famous, prediction that Allan, worked together. There was also some, simultaneous work on STM spectroscopy by Ivan Trey and by the group of Eric Suarez-Molay in Chile. And this was something that, sounded crazy. This electrons are going to become flat. The electron velocity is going to go to zero. Who knows what would happen? It seemed very esoteric at the time. If you do an actual calculation nowadays, including also some extra relaxation, and so this is, this was a cartoon here. This is an actual calculation. These are the flat bands. These are the other remote Moray bands. Okay? If you look at where those electrons like to sit when you, in real space, when you fill, when you put your chemical potential in these flat bands, they like to sit in certain regions of AA stacking, and they like it less on the regions of AB and BA stacking. So you end up schematically with something where twisted bilayer graphene becomes this solid, where you have some regions of AA stacking separated by about 13 nanometers where the electrons like to be. And this is sort of going to play a little bit, be a little bit of an analog of a, triangular Fermi-Hubbard lattice in cold atoms language, okay? Except that I have a lot of quotes here, the question, triangular, in reality, this thing is honeycomb because AB and BA is not the same. And it's not really Fermi-Hubbard lattice because these electronic properties of twisted bilayer graphene have a special topological structure that prevents a direct mapping to a vanilla Fermi-Hubbard lattice of the cold atoms type, okay? But this was sort of the inspiration, for a lot of the work that we were thinking about. Now, in 2018, my group, we discovered that when you fill, when you put an integer number of electrons on holes per Moray unit cell in the system, okay, you have correlated insulator states. And if you dope a little bit away from those, you get electrically tunable superconductivity. Yeah? This is something that was very unexpected and that drew a lot of attention. And I want to tell you a little bit now about some of the highlights of what has happened since. So we published this in 2018. And then I'm not going to comment on the highlights from theory because there are thousands of theory papers. It will be too hard to actually, analyze even a small fraction of them. Needless to say that not all of them are right, but plenty of Allans are actually right. Okay, so Allan has been a major contributor to this field. I would say that in the rush to get things published and so on, a lot of people did approximations or did things which were a little bit questionable, but Allan was always a little bit more careful and on average much better at hitting the right directions and the right key points for the community. Again, Allan has always been a beacon, providing inspiration for all of us to follow and see where things are going, and I think it shows in this field. Now, so experimentally, some of the things that have happened is that, as you know, nowadays in condensed matter physics, a lot of people are always commenting on the fact that, things are not reproducible or not, actually outright not true, like, some of those famous room temperature superconductors from the past few years. This community, not only in my own group, we have reproduced our own results, but many groups have independently reproduced our results and extended them to other very interesting systems. In fact, in the rest of the highlights I'm going to show, you're going to see that very often papers appear in multiples 2, 3, 4, at the same time. Many groups are working on this. There's a lot of competition, and results pop up at the same time by multiple groups independently. Okay, so that's actually something which is very nice because it allows a lot of progress because people immediately see that this is actually real. That things are being simultaneously reproduced by many people. So the first groups to reproduce our results were, a collaboration between the group of Corey Dean at Columbia and Andrea Young at UC Santa Barbara. They did something very interesting. They could, they checked, first they made a magic angle twisted bilayer graphene device, and they saw that it has correlated insulators and superconductors like we did. But then they made a device which was off magic angle, a little bit larger, 1.27 degrees, as you can see here. They measured, they didn't see any correlated insulators or superconductivity. But remember, this magic angle condition, this flatland condition, depends on the interlayer tunneling. So what they did is they applied pressure. When you apply pressure, the magic angle becomes a little bit larger. So they knew which amount of pressure they had to apply, because together with Tim Kaxiras at Harvard, we had calculated already the pressure dependence of the magic angle condition. So they went to the right pressure, they applied, they cooled down, they measured, and they saw correlated insulators and superconductivity. Okay, so that was a very nice demonstration that indeed this process is tied to the flat band condition, which is tunable by pressure. And then in a paper, from the group of Dimitrij Efetov, back then at ICFO Spain, now in Germany, but with Allan as a co-author. Again, another thing that I want to emphasize and comment on is the fact that Allan is not only a great theorist per se, he is an extraordinarily fruitful collaborator of many experimental groups. So we all really appreciate very much our discussions with him and his input. So, this paper also reproduced, the basics and found some additional superconducting domes. So by now, robust superconductivity in magic angle bilayer and many other systems, Moray systems, has been reproduced by many, many groups and extended. Okay, now the list keeps going because more people are joining. So another thing that has happened, and this I already mentioned in a previous slide, is that we have seen plenty of other phenomenology and phenomena and phases characteristic of strongly correlated quantum materials. So for example, strange metal behavior, nematicity, Fermi surface reconstructions and cascades of phase transitions, pseudograph physics, etc. I will show this because it's going to appear a bit later in the talk. Okay, in 2020, both a collaboration between Shahal Indani and my group, and also work with Ali Yazdani, STM work, we saw that at these integers of 1, 2, 3 electrons or holes per Moore unit cell, you have actually a phase transition at each of them. Okay, so there is a cascade of phase transitions, indicating Fermi surface reconstructions and also polarization of your electronic system. You go from having spin and valley degeneracy to having only one of them or the other, or combinations. Okay, so that was measured both in the inverse compressibility, these bumps at each integer. Those are the cascade of phase transitions, and you can see them also in STM very nicely. As you can see, papers, 2 at the same time, they were published back to back, and that's going to happen in all the highlights that I'm going to mention. People have discovered many other correlated systems. It's not only magic angle twisted bilayer graphene, but you can, if you take 2 layers, it can be ABC trilayer graphene aligned to HBM, another interesting Moray system. Magic angle twisted bilayer graphene, so it's 4 layers, but 2 twisted on top of 2. These 2 0 degrees, we call that twisted bi-bi. Of course, the transition method chalcogenides, Moray systems, you heard yesterday from Xiaodong, I'll also mention his work, these are extremely interesting systems too, where all of these, physics, corrective physics is being explored. One of the most interesting developments was the observation of ferromagnetism, anomalous hole, and integer and fractional quantum anomalous hole physics in these Moray systems, because that brought the role of topology front and center to the problem. So, in fact, something which is very nice is that in this Moray quantum matter field, it has meant the merging of several condensed matter physics communities, which before they were not interacting that closely, I would say. On one hand, you have people that did, 2D van der Waals materials and heterostructures, graphene, like myself, we're studying just graphene by itself or other 2D materials. Then the people that study traditional strongly correlated materials, like cuprates and pnictides and heavy fermions, etc. And then people that study topological condensed matter physics, integer and fractional quantum Hall effect, topological insulators, bisemi metals. All of this physics comes together in this Moray quantum matter. So it's really nice to interact with many people that I didn't used to interact with before. Already in 2019, my colleague Senthil, we proposed, a number of Moray heterostructures that would exhibit, nearly flat Chern bands. Okay, there was a lot of other work also on the topological properties of twisted bilayer graphene. And within a few months, the group of David Gohaber-Gordon reported this very strong anomalous Hall effect, okay, indicating that this was a magnet. Twisted bilayer graphene aligned to HBN, magic angle graphene aligned to HBN was a special type of magnet, an orbital magnet. And just a few months later, the group of Andrea Young reported this quantized anomalous Hall effect, so quantum Hall effect at zero magnetic field in this system. This was already extremely interesting, but then, of course, as you all know, last year, this became even better. Okay, so Xiaodong Xu, and he spoke about this yesterday, he showed the fractional quantum anomalous Hall effect in twisted bilayer MOTE2. Okay, very interesting. And then my colleague Long Yu a few months later, demonstrated this in a more heterostructure of rhombohedral pentalayer graphene aligned to HBN. Yeah? And I should mention that there had been a lot of especially theory work early on fractional Chern insulators, but it was a little bit abstract. We didn't have a clear experimental realization, how to do this. But then when Moray systems came into the market, it was immediately very rapid progress from prediction of fractional Chern insulators in Moray systems to then realization experimentally. So that was actually, again, I think in this community, there's a very fruitful interplay between experiment and theory, and very fast also. So lots, because these systems, these Moray systems are at the surface, it means they can be investigated by lots of local probes, okay? So almost every, local probe technique has been applied to it: scanning tandem microscopy, scanning nanoscreed, scanning single electron transistors, scanning near optical microscopy, scanning transmission electron microscopy, and even new techniques have been invented to look at these materials, like the quantum twisting microscope. Okay? So let me highlight here two of these results. One is, this very recent, this past year, study by Ali with scanning tandem microscopy. Ali and his group members, they did, took these images of very high quality magic angle twisted bilayer graphene. But, so this is many nanometers by many nanometers, right? You can see the Moray pattern, the AA regions, the AB. But they took these images with atomic scale precision so that they could look at the wave functions at the atomic scale. And it turns out the different many-body phases of magic angle twisted bilayer graphene, for example, the correlated insulators, have an imprint locally on the atomic scale wave function, okay? So in this study, Ali and colleagues, they could narrow down, among the many, many options for correlated insulator states in the system, they could narrow them down very severely so that there's now much, very good amount of data for theorists to continue thinking about this problem. And this was really very interesting. And then the group of Shahal Ilani published this new technique, which I think is quite revolutionary, the quantum twisting microscope, where now, for the devices that we and the majority of the community has been making so far, you can choose any angle that you want between the two sheets, okay, with very high precision. But once you make the device, that angle is fixed. So what Shahal and collaborators did is they decided to put one graphene sheet on a substrate, the other graphene sheet on the tip of an atomic force microscope, and they could come with one on top of the other. And the nice thing is that this atomic force microscope tip, they can rotate it, and they can rotate it in situ. Okay, so now you have in situ electronic control of your twist angle. Okay, and that was tremendous. For example, they could do something which is effectively ARPES, angle resolved photoemission spectroscopy, of the electronic structure of twisted bilayer graphene. This is what I'm showing here, but they're doing this with 2 to 3 orders of magnitude higher energy resolution than actual ARPES. And you can do this in the presence of a magnetic field. You can vary a lot temperature, etc. And you can scan actually and do locally all of this. So this is something which is a very interesting development. And these were room temperature data, but now I know that Shahal recently is beginning to show actually their lower temperature data, and it's extremely interesting. So I think there will be many developments coming from this. Okay, and the last thing that I want to say is that you don't have to stop at 2 layers on top of each other. You can do 3 and 4 and 5, and there's magic physics happening in all of this. Okay, so back in 2021, the group of Philip Kim and my group, we published back-to-back papers with the discovery of strongly coupled superconductivity magic angle twisted trilayer graphene. It's a very strong superconductor. I will talk a bit about twisted trilayer graphene in a moment. And the following year, again, several groups, as you can see, the group of Stefan Natchmerch and my group, we published about superconductivity in magic angle twisted tetra and pentalayer graphene. And the group of Emmanuel Tutuk, who's here, published also very interesting results on correlated physics on these 4 and 5 layer systems. As you can see, again, these papers appear in multiples of 2 or 3 by different groups. So it makes it, a very convincing case very rapidly for people to look at their properties. Very good. So with that, these are just some of the highlights, okay? A lot of other things have been going on. And I'll be happy to discuss about this. Let me go into more, specific data. In fact, these are unpublished data that I wanted to show to you today. So superconductivity in magic angle twisted N layers graphene, could be bilayer, trilayer, tetralayer, appears under certain conditions. And since we have a lot of tunability, we have narrowed down these conditions, quite well. For example, it seems to appear or be most robust, strongest in systems which have C2T symmetry, okay? And at least all of the systems who have the C2T symmetry exhibit this superconductivity and very robust. It happens, in regions where, because we have information about this cascade of phase transitions where the symmetries of the system are broken, okay? In particular, it typically appears in regions where you have, either two electrons. It's stronger in regions where you have 2 electrons or 2 holes per Mora unit soil. 2 electrons, 2 holes plus some additional doping, okay? Plus some extra electrons or plus some extra holes. And it's also unusual because it is likely non-singlet, the tunneling spectroscopy curves from experiments, by Ali and by Stefan Nachbert show these V-shaped tunneling curves. And it exhibits rotational symmetry breaking for some, depending on the symmetry properties also of the structure. So it's a pretty unusual superconductivity. And I would say it's a bit more mysterious than so far the topological properties, where theory and experiment have very quickly converged, and they have looked at, theory has predicted, experiment has demonstrated, experiment showed first, and then theory very quickly came and explained. Superconductivity is still a little bit mysterious. This is a simplified phase diagram of magic angle, bilayer graphene in this case, but all of them have very similar phase diagrams. This is in filling factor or doping. Okay, you can see correlated insulator at 2 holes per Mora unit cell, then a superconducting dome, and a pseudo gap. There are all kinds of quantum hole insulators and chain insulators of various types, which can appear. Now, something that has been a little bit difficult in this field is that because there are many competing many-body states close in energy, and because you also have, some inherent disorder, for example, twisting disorder, although the basic features have been reproduced many times by many groups, sometimes doing detailed comparisons between different devices or different regions of the phase diagram, okay, has turned out to be a little bit difficult. And that means that it's very convenient, some things that you can find with one technique, it's harder to see with the other and vice versa. So what we thought is, it would be very nice to use a multifaceted approach, to correlate physics of different phases, and in the case of superconductivity in particular, it's very likely unconventional. There are many indications that it's unconventional. And how, can we do transport and tunneling spectroscopy and compare just in a single device, so that you can correlate all these features in the same device? Okay, that's something that has not been done. So let me tell you what's the structure that we fabricated. Okay, so it is pretty complex, as you can see, with many layers. It has 2 gates at the bottom and at the top. So it's a dual gated structure. Okay, and then the active regions are, we have 2 magic angle tri-layer graphene sheets. So 2 3-layer stacks. Okay, the bottom magic angle tri-layer and the top magic angle tri-layer. Now, separating these 2 magic angle tri-layer sheets, there are 3 layers of HBN. That's a nanometer in thickness. That's going to be a tunnel barrier between these 2 magic angle tri-layer sheets. Yeah? And then we have a thicker HBN where in everywhere except for a region, there is a hole, okay? So in that region where there is a hole, here the contrast is a little bit bad with the light, but in that region of a circle of a micron in diameter, there is a hole here. So the top and the bottom magic angle tri-layer graphene are connected by this tunnel barrier, okay? But in the electrode regions, they're separated by this thicker HBN, okay? So it's a little bit complicated, but I hope most of you are following the structure. So this means that now, because each of the magic angle tri-layers has hole bar shape, we can do intra-layer transport of the properties of the magic angle tri-layer graphene in each of the 2 layers. And we can also do interlayer tunneling experiments so that we can probe with one the other, okay? So we can do transport in plane in each of the layers, and we can do transport between the layers, which is actually tunneling because we're going to the tunnel barrier. Okay? So let me show you the intra-layer transport for each of the layers, okay? So, the resistivity as a function of back gate and top gate. This is the resistivity of the top layer. That's why these features are mostly vertical. In reality, there's a little bit of an angle, but it's mostly vertical because the bottom layer, the bottom magic angle tri-layer screens, the back gate. So this is why the features. you have, insulating peaks near nu equals 0, nu equals plus minus 4, and superconductivity for 2 electrons to holes per molar unit cell plus extra doping. Okay, that's what you expect. And then if you look at the resistivity through the bottom magic angle trilayer graphene, you have also superconductivity here, and the charge insulating point. This time the features are mostly horizontal because the top magic angle trilayer graphene screens the top gate. Okay, as you can see, there is a little bit of an angle, and we have less range with the back gate and with the top gate. Okay, accessible. That's why you see only a portion of the phase diagram here. Now, there was a good reason to choose 2 magic angle trilayers, even though this is a very complex thing. But for the rest of the talk, I'm going to use the bottom magic angle trilayer as a tunneling electrode in the normal state. So I'm going to choose my backgate voltage here so that the bottom magic angle trilayer is in a normal state, featureless, relatively featureless normal state, metallic state, no superconductivity, no insulating. Okay. And with this bottom magic angle trilayer graphene, I'm going to explore the top magic angle trilayer graphene, superconductivity, etc. Okay. So let's choose, this gate voltage in the bottom gate. So this is a normal electrode now, and then I'm going to sweep, the top gate so that I'm making it around this. Okay. So again, the bottom magic angle trilayer is just a tunnel probe for the top magic angle trilayer. If I measure the differential conductance as a function of interlayer bias, this is equivalent of the STM tip voltage and top gate voltage, you can see these features, which are very reminiscent of the STM studies of magic angle trilayer graphene, where you can see the cascades of phase transitions, okay, etc. Let me show you here. These are the cascades of phase transitions that occur. And then you have these gap regions near there. Don't worry, I'm going to zoom in a lot of detail now, okay? In fact, this is over very large energy scales. I'm going to zoom in to just a few, hundreds of a millivolt, okay? And this is the differential tunneling conductance. You can see these dark regions, regions of very low differential tunneling conductance. And I can simultaneously, or right before or right after, I can also do it simultaneously actually, measure the resistance through the top, the intralayer resistance through the top magic angle trilayer graphene, okay? And that, shows me this, okay? I have the resistivity as a function of top gate voltage. And I have these regions of superconductivity, 0 resistance. These regions are correlated in doping with the regions where I see this gap in the tunneling spectroscopy, okay? And you can look at, the traces, for each of these things. We're going to look at these traces in much more detail now, okay? You can see that there's this gap region here and here. So these are the first simultaneous transport and tunneling spectroscopy measurements of magic angle graphene, okay? Now, let's look at all of this in a bit more detail. In fact, I'm going to zoom out a bit in energy, intermediate between this very large energy scale and this middle energy scale. So we look now again at the tunneling conductance, a function of top gate voltage and interlayer tip bias, planar tunneling bias, okay? So what you can see,
Pablo, we are a little behind of time.
Oh, we're behind. Oh, okay. I'll just go fast. So we have 2 regions with 2 types of gaps. Okay. If you take a trace, you have actually a low energy gap and a high energy gap, 2 distinct features. Okay. These 2 gaps have energies about 10 times different. If you do transport through the same structure, you can see how at what temperature the resistance deviates from 0. And if you do tunneling spectroscopy, you can see that the inner gap very rapidly disappears with temperature, okay? Whereas the higher energy gap, it has a very slow dependence on temperature. This thing disappears on the scale of TC. This one takes much longer, okay? And you can, in fact, characterize that by rapid evolution of the low energy gap and very weak evolution with temperature at the high energy gap. This high energy gap, in fact, behaves like a pseudo gap, okay? While the low energy gap behaves like a superconducting gap. You can do the same thing with tunneling and perpendicular magnetic field. This inner gap, okay, evolves very fast, whereas the high energy gap barely changes with magnetic field up to pretty high energies. Again, this is consistent with the pseudo gap behavior, whereas this is the superconducting gap. let me just point out that indeed this, be perpendicular of these higher energy gaps, were measured before in tunneling spectroscopy, by Allan and Stefan at Perch, and they exhibit very similar behavior in energy scale and dependence with magnetic field as what we see here, and also the temperature dependence. And it's more consistent with what a pseudo gap would do also in cuprates. So if you look in detail at the, superconducting gap, which is the lower energy gap that you see in there, you can see that it starts to deviate very quickly. This gap fills very quickly, even before, well before there is any deviation from zero resistance state, okay? You can analyze all of this by using the same procedure that was applied to cuprates, for example, okay? I'm sorry, I'm going a little bit fast through this, but you can fit this thing, with various, superconducting distributions, and it fits much better to a nodal than to an S-wave superconductor, okay? You can do the temperature dependence of this, this gap fills very quickly with temperature, which is consistent with what you expect for nodal behavior, where you don't have, you immediately start exciting quasi-particles with temperature. Okay, I'm sorry I'm going so fast through this, but we can, of course, do all of this electrically dependent and check the dependence of the superconducting dome, and it's all consistent. Both the high energy gap, the pseudo gap, and the superconducting gap have a doping dependence, which has the same train as the superconducting dome, okay? So most likely the high energy gap is connected to superconductivity, even though it's not the actual superconducting gap as established by phase coherence in the system. Okay? And with this, let me just show you that there is this Bolovic effect, which is also a rapid increase of the tunneling density states, when you apply a perpendicular magnetic field. Again, this only appears for nodal superconductors. And in plane magnetic field dependence also shows this rapid increase, which is again consistent with the nodal superconductivity. So with this, I'll skip the summary, okay? I will say that, related work on nodal superconductivity by Princeton and by Caltech, and also by recent kinetic inductance measurements by Philip Kim and ourselves, and by Will Oliver and ourselves, also point in this direction of a nodal superconductivity. I want to thank my group members. This was largely the work of Jane, who is now a postdoc with Ali, actually, and Shuwen. And thank you very much, Allan, again, for all your contributions. Thank you all for your attention.